Okay, I'm going to present underwater sound signatures of offshore industrial operations. So let me first acknowledge my team. I've had about a quarter of my team contribute to this talk. And yeah, all right, so I'll be talking about sounds from pile driving, from vessels, small to large vessels, from dredging, drilling, seismic surveying, as well as aircraft. Starting with seismic surveying and airgun arrays. These are used for marine reflection and refraction surveys and exploration geophysics. So basically, an airgun is a chamber, and you fill it with highly compressed air, you put it underwater, you suddenly open it up, and you're creating a gas bubble underwater. It rapidly expands, it overshoots above the ambient pressure, and then it collapses again. So you've got an oscillating air bubble underwater that sends a pressure waveform into the seafloor, reflects off different seafloor layers, and then on hydrophones or streamers, we measure the reflected sound, and from that we can draw conclusions about what is underwater. Now, you would not normally use a single airgun except for special cases, but mostly arrange your airguns into arrays. And there's an image of an example array here. You've got different airguns of different volumes arranged in an array so that we can beamform the acoustic output and steer the sound vertically down into the seafloor. And now that the sound is working, all right. So basically, the sound from airgun arrays is pulsed, broadband sharp pulses happening every few seconds. Looking at the acoustic waveform in more detail, in the left plot here, we see the oscillating pressure pulse just from a single airgun. There are certain types of airguns, GI guns, where you have a second chamber. You release that shortly after the first one, and that is to dampen the bubble pulse. The spectrum of these is broadband. Now, in the right picture here, we see the directivity pattern in the horizontal plane of an airgun array, and it obviously differs depending on frequency. Now, if you add the acoustic energy across frequency, then you're going to get the noise footprint of this airgun array. So in this picture, we've got northing versus easting, and you're looking sort of an aerial view of the maximum sound exposure level over depth. And the reason why we take the maximum over depth is to be conservative, but also because we, of course, have a directivity pattern in the vertical plane. So this is a figure of a depth range slice. So you've got depth on the vertical and range on the horizontal. The black line is the bathymetry, and there would be an airgun array somewhere in the water here. And then what is plotted is the sound exposure level in the water as well as underground. So now, as I said, when you're close to a seismic array, the sound is broadband pulse, and there are quiet gaps in between. But as you get further away from a seismic array, you have multipath effects, so your pulses smear out. And in certain environments, you also get some really pretty frequency dispersion, which might not turn your broadband pulses into frequency modulated sounds. So in these two spectrograms are recordings in Australia. The top one would be over a fluid seafloor, and the bottom one over a rigid seafloor in shallow water. And you can see that the seismic or the energy from seismic airguns remains at low frequencies but turns into frequency sweeps. All right, so of course the take-home message here is in terms of impacts on marine animals, they might differ depending on where the animal is. If it's close to the array, it will experience high levels broadband sound, but with quiet gaps in between, whereas the further away you get, the more these sounds become continuous. All right, pile driving is another pulse source, and used obviously in coastal regions for construction, but also subsea piling is happening to install moorings in deep water for offshore operations. So pile driving is quite a horrible and complex source. Basically what's happening is you've got the pile in the water, you hit it with a hammer at the top, that causes a little deformation which travels down the pile, gets reflected, travels back up, and then down again, and so forth. And while it does that, it radiates the pressure in a Mach cone in the water, but you also have P and S waves in the ground, and interface waves, your Schulte waves. Now, how on earth do you model that? Well, you can use finite element and difference methods to model the near field, and then you need to couple that to, for example, normal modes to estimate your long-range propagation. Now, what is interesting here is that the sound pressure field in the water depends on what the seafloor is like. And then it's this little animation. We have three different types of seafloor. There's fluid sand in the left picture, then we've got elastic sand, and then we've got rock, elastic calcarenite. And what you're going to see, if it works, is the pressure field in the water and in the ground, and you'll see that it actually is quite different. And it didn't work. Let's try that one again. Oh, I don't know. All right, last one. Let me just jump over it. There it goes. Who knows? All right, so what you can see here, and I'm too slow and I'm trying to catch up. At least let me point out the Schulte wave here, the interface wave. It's here, it travels faster, the more solid, the more dense the seafloor is. And here it is traveling slower, and we don't have it in the fluid seafloor. All right, next slide. So here are just a few snapshots. So first 4 milliseconds after you hit the pile, the field in the water actually differs not that much with the seafloor. But then once the first reflection comes up, you can actually see the difference between the three cases here. So in the hard seafloor, you can see the spherically reflected wave, which you hardly have in the other ones. And the other thing to point out are these interface waves, here the Schulte waves, and they can actually carry quite some energy. And there's been hardly any studies on what these things might do to sessile animals. All right, moving on. Dredging, a form of excavation, involves the cutting, grabbing, and throwing away of seafloor material. So there are at least 24 different types of dredges, and the sources, and some of those are vessels are self-propelled, others are barges and need to be towed into position. And then, of course, the sources of noise relate to the traveling and positioning of these dredges, and then the cutting, uplifting, and dumping of the material. So in this recording here, we had a dredger in shallow water, as there mostly would be. And because of the shallow water, you have hardly any energy at low frequencies. Moving on to drilling. All right, in this figure here, we have recordings of one drill rig with 3 recorders at different ranges. And these, in the top plot, we have got 5-minute averages of the sea noise spectra. So what you can see here is that the drilling spectrum consists of tones below 100 hertz. And as you get further away, at 10 or 20 kilometers, the spectrum disappears in the ambient noise in this case. Now, in this picture, which is a bit harder to get your head around, I've plotted the percent of time that the broadband drilling spectrum, there's the mouse, is above certain thresholds. So the way to read this, for example, if we look at curve 16 or 17, and all of these are just from all sorts of drilling operations at different ranges and averaged over different numbers of days. But if we just picked out 2, like 16 and 17, these are both of a drill rig that was 4.6 kilometers away. There was a rig tender also operating in one of them. And then the way you'd use this graph is if you're interested in the median levels, you go to the 50th percentile, and the broadband level in this case at 4.6 kilometer range would be somewhere between 107 and 112 decibels relative to 1 micropascal. All right, coming to ship noise. If you just type a vessel type, yeah, into Google, it'll come up with pictures like this. So there's like dozens and dozens of different vessel types. They range from the small few meter personal watercraft to super tankers and then FPSOs of a few hundred meters length. What they have in common, however, is the type of noise that vessels generate. So ship noise from motorized propeller-driven ships is due to machinery noise, so your diesel engines and main motors that transmit through the hull into the water. Then we've got propeller cavitation noise, propeller singing, as well as propeller-induced hull resonance, and hydrodynamic noise from flow past fluid cavities and past cavities, plates, and appendages. Now, if your vessel travels at a speed higher than the propeller cavitation inception speed, then propeller cavitation is typically the strongest source. And it's related to the noise of vibrating and collapsing bubbles yet again. So conceptually, cavitation is similar to boiling, except in boiling, you create the gas bubbles due to a rise in temperature, whereas cavitation is due to a fall in pressure at the tips of the rotating propeller. All right, some recordings of propeller noise from large vessels. And let's just move straight onto the spectrogram. So here's a spectrogram of a large vessel moving past one of the CTBTO recorders of Western Australia. You've got the frequency versus the time here. You see the engine tonals. And then the broadband cavitation spectrum turns into this pretty Lloyd mirror pattern due to repeated constructive and destructive interference of the direct travel path and the surface reflected travel path. And your point of closest approach is at the minimum of the Lloyd mirror pattern there. All right, in the next few slides, I've got a few source spectra in 1/3 octave band levels of large vessels. So these are merchant vessels. You can see the broadband levels will go up to 190 decibels or more. And these are cruise ships, also that loud. When one compares source spectra from different studies, there's one thing to watch out for. So these are all radiated noise levels. What that means is the ship was recorded at some range, and then a geometric spreading term was applied to compute the source spectrum, so a 20 log R. In some other studies, people might use a sound propagation model and actually end up with a monopole source level. So depending on the environment, these can be quite different. So the monopole source level would have included the environment and the surface reflection, whereas the radiated noise level would not. So that is something to keep in mind when one compares source spectra across different studies. Going from the big ones to the little ones, the rigid hull inflatable boats. These are support boats used by marine and offshore industries, coast guards, water police, sea rescue, as well as whale watching companies. And we recorded some of those back then in Canada when I was still at Fisheries and Oceans, but also more recently in Australia. So in Australia, we were lucky we had full control over the boat, the course, and the speed, so we were able to investigate the spectrum in a bit more detail. So we knew the rotation, the RPM of the engine, we knew the RPM of the propeller, the gear ratio, as well as the number of blades. And if you have that information, you can actually identify the tones you see in the spectrum as the propeller and the engine tones plus certain harmonics. So then in the right plot here, the straight lines are all the theoretical lines as a function of engine RPM. What do we expect the tones to be? And then the circles are the actual measurements. And there's quite a pretty lineup. All right, so then here we now have, I just lumped 142 recordings of ribs. These were recorded at 3 different sites, and they traveled at different speeds at the 3 sites. So I sort of have a trimodal distribution, but nonetheless, I just plotted them all on top of each other. What you can see is that for those that go really slowly below the propeller cavitation inception speed, you see the tones, and the level of the tones doesn't really change much with your RPM. However, the broadband cavitation spectrum, of course, goes up in level as your speed increases. Jet skis, now we certainly will not have those offshore by industries, but they're just a pretty thing to listen to. And that just sort of fits the model. With jet skis, you also have your Lloyd mirror patterns, and you also have all of your little tonals from an impeller in this case. They're just much higher in frequency, up to the kilohertz range. Now, from the little things to the really big things, floating production, storage, and offloading. On the northwest coast of Australia, for 2 decades, we had 6 of these FPSOs operating in fairly close proximity, and we recorded them both at JASCO and at CMSD, and then we pooled our data and published the lot in JASA. And basically, there's so much happening on these vessels, you can't really identify in your spectrum what the contributors were. So at the end of the day, you get a log from the FPSO, and then it'll say, you know, at 10 a.m. we did water injection downhole and diesel-generated testing, and gas flaring on the starboard side, and gas compressors running on the port side, etc., etc. And then there might be offloading, which involves tankers and tugboats and then dynamic positioning. So there's just so much happening that it's impossible to say what contributes what. So we took a statistical approach, we lumped all the data, and we reported power spectrum density percentile levels as well as percentiles of 1/3 octave source levels. All right, FLNG, floating liquefied natural gas, something of the future. However, the first one is going to go into operation in Western Australia at the end of 2017. So there's a lot of processing happening on these vessels, and the sound radiates through the hull into the water. You also have waterborne sound as well as groundborne sound that radiates back into the water. Now, thanks to Buzz's talk, I don't have to spend any time on this one. We have a few recordings of flow noise through choke valves and flow lines, but we don't have any recordings of any other subsea seafloor infrastructure. Finally, aircraft. So if you're a receiver underwater and you have something flying overhead, you will hear it. The sound transmits straight through the air-water interface, except when you're now moving away horizontally. So if you're as far away that the direct path has an angle of incidence from the vertical of less than 13 degrees, you're going to get the direct path. If it's greater than that, you've got total reflection. So if your receiver in the water is even further away horizontally, you're only going to get sound by multiple reflections from the seafloor and the sea surface. Anyways, we recorded helicopters and airplanes and drones underwater. There is a small airplane flying 175 meters above a receiver in 7 meters of water, and we just cannot get rid of those nasty snapping shrimp in Australia. And here is a helicopter at the same height. Yeah, we also recorded drones. They're obviously quieter, so power spectral density levels are somewhere between 80 and 90 decibels, but you still hear them above ambient noise. So then the final slide, sonars, the only thing I want to say about those is that the manufacturer will give you a source power level for the sonars and the nominal frequency. However, most of these will have obviously side lobes and maybe even harmonics. So when you record them, the power spectral density to the nominal frequency will typically be quite less than the output power that is specified by the manufacturer. All right, so I've looked at a couple of different types of sound sources individually, and as the previous presentations already made the point, the question is cumulative noise around multiple operations, and not just from offshore petroleum, but also mining and fishing vessels and defense operations, tourism, etc. And then ultimately, of course, what are the effects on animals from cumulative noise? But that's a topic for a different talk. Thank you.